We'll talk about address resolution, which is generally known under the acronym ARP, even though in IPv6 it's called differently. And then we'll talk about host configuration, which you've already encountered in Lab 1, but we'll talk again about it, and we'll mention a few features of the IP packet format that are of relevance. IP is originally conceived as a mechanism to interconnect local area networks, which Ethernet switches, for example. And this is visible in the need for performing what is called MAC address resolution. We know that if we we know that the IP algorithm says that if I am a router, for example, I am this machine here, ED2 in, I have a packet to send to that machine given by the blue arrow here. Yeah, I'm learning to use this pointer. The rule says, because the destination is on the same subnet as one of my interfaces, in other words, I am directly connected to that system. Directly connected from IP means I am on the same local area network. Then I should send directly. And what does send packet directly mean? That's the question. Well, the answer is send in an Ethernet frame, if it's Ethernet, that has MAC destination address, the destination of the final machine that we want to reach. That's what send directly means, as opposed to send indirectly, which would mean send to a router in between. But to do that, we need to know the MAC address of the destination. Knowing the MAC address is impossible by just observing the IP packet. So when this router, ED2IN, has a packet to STI SUN, it sees just an IP packet header. Of course, it has received a packet over Ethernet headers, but the Ethernet headers have to do with the previous hop, so it doesn't contain the MAC address. So this information is not available just by analyzing the packet. So we need to do something which is called address resolution procedure. So the first important thing to understand is what is the goal of the address resolution procedure, or in IPv4 it's called the ARP protocol. The goal is to answer the question, I have a packet to send to an IP destination address. I know this IP destination address is on the same subnet as my interface, one of my interfaces. I know this by analyzing network masks. What is the MAC address that corresponds to this IP address? How can we solve that? We could imagine zillions of ways to do it. We could do like for the DNS, we could have a directory server somewhere on every local area network. We could have a database with all the MAC addresses that correspond to all the IP addresses. It is done in some enterprise networks, but the default solution is not that one. The default is to use broadcast as opposed to directory service. That's something we will find very frequently. Whenever you have to do a directory service, you can always replace it by a broadcast. A directory service means you have a big table where all the mappings that you're interested in are written. Broadcast, by opposition, means whenever you need to know a mapping, you ask the question to everyone. And then the people concerned will answer, hopefully, if there's no attack on your network. The ARP protocol uses the broadcast idea. So it works in the following way. First, we are at this stage, ED2 minus IN wants to know what's the MAC address that corresponds to a given destination address. It creates an ARP packet, which for IPv4 is not an IP packet. So it is a third example of an Ethernet protocol. We have IPv4. By Ethernet protocol, I mean what are the things that are carried inside Ethernet frames. It can be an IPv4 or an IPv6. Well, ARP is also a special packet, which is not an IPv4 packet. So there is no IP destination address, IP source address. It contains a destination MAC address. It's an Ethernet frame. The destination MAC address is the broadcast address, all ones, in hexadecimal, all F. And it contains a number of fields that you can pretty print when you do Wireshark. But in particular, it contains inside the payload the IP target destination address. So this packet is containing a question: who has this IP address? Please give me your MAC address. So this is what we call the target address. It's not an IP packet, it's not a destination address. It's part of the message that's contained in the payload. Now it's broadcast, and that's a very essential feature. Inside the LANs, you see broadcasts. And this is the most frequent broadcast that you see inside a LAN. Broadcast means everybody receives it. STI SUN1, LRC-PC2, ED0X. They all receive it. The only interesting case is STI SUN1. But of course, nobody knows who is STI SUN1. So we use broadcast. Everybody receives it. If there is no misbehaved device in your network, only STI SUN1 will respond. This address, this Ethernet packet is broadcast. That means the Ethernet adapter will copy it. An Ethernet adapter, when it sees an Ethernet packet with destination address broadcast, it thinks, oh, that's for me, because that's for everyone. So it will copy the packet and forward it to the operating system. The operating system will see this is an ARP packet by looking inside the Ethernet packet, and will do the correct thing, which consists in doing an ARP reply. Inside the ARP packet, there's the question, who has this IP address? The operating system says, oh, that's me. I have an interface that has this address. The operating system knows what are all the MAC addresses and IP addresses, and you've seen some of it already, and we're continuing observing in the labs using various commands like ifconfig and others, what are all the MAC addresses that are available. So it will respond with another ARP packet that is now targeted towards the EDI, this one, the correct one. Now we don't need to broadcast. It's not an IP packet, there's no IP destination address, but there is a MAC destination address, which is whoever was the source address in the request. So in that case, ED2-IN. And inside the message, there will be who has this MAC address. And now, and only now, ED2-IN, the router, is able to forward the IP packet because now it knows the MAC address. Do we do this for every IP packet we have to send? Of course not. That would be a bad idea. That means whenever we have an IP packet to send, we need first to do this HARP handshake. That would be very expensive. So there is a cache where the this is annoying. I'll try to remove that when I'm more expert in PowerPoint. Of course, the result of what we call this mapping, the correspondence between MAC address and IP address, is kept locally in a table, which we call a cache. A table is a cache versus a directory when it's learned on the fly. So a cache is something temporary, where you put information that you can reuse, but has no authority. It is not something that you can be 100% sure about. And in particular, invariably with a cache comes the concept of a timer. The entry in the cache has some time to live. After some time, it will expire and will be deleted. It will not expire if the cache is confirmed. And we get a confirmation if we can observe traffic. So typically when you send one packet and you get a reply, you will often have many, many replies. So if this router is sending traffic to this one, if it's a single packet, then the cache will expire after a few minutes, which means the next packet will need to do all that ARP reply and the request again. But in most cases, there is traffic flowing between the two. If there is a lot of traffic flowing between the two, every packet that is received by the router contains an IP source address received from STI SUN1, contains an IP source address and a MAC source address. So the router will take this as a confirmation and will refresh the timer of the cache. So that we need, in the best case, to do it only once, very, very few times. Yes?
So if the broadcast is disabled in a LAN, then is ARP protocol still used? Like you said that within EPFL LAN, the broadcast is disabled. So is it still used?
So the question is the broadcast sent to the whole LAN? Yes, but the question is what is a LAN? So local area network is a very, very specific term in the TCP IP terminology. It doesn't mean something inside the building or something like this. It has a very, very concrete term. It means a set of devices that can talk to each other without going through a router. That's a LAN. Okay? EPFL is not a LAN with that terminology. EPFN is a complex network with hundreds of LANs. So this broadcast is broadcast inside the LAN. It doesn't go through the router. Right. So it will not flood all EPFL. A LAN, typically at EPFL, is one floor of a building. So it will flood all the machines. It will flood all the machines in that floor. Question?
Why the choice has been made of doing a broadcast instead of having a directory?
Why is the choice of a broadcast rather than directory? It's for simplicity and plug and play. The MAC layer, we'll come back to that in 1 hour, is plug and play. The MAC layer means you go to Migros, you buy a box that is a switch for us, perhaps it's called a different name by the Migros people. You connect 3 computers with Ethernet cable, or your TV, desktop box, etc., and it works. It's completely plug and play. You don't have to type in to set up a directory service, configure a password. And so that's in order to be plug and play. So it's completely transparent. You connect those machines together. You have to configure the IP layer. This one is not plug and play. But as soon as they're connected by an Ethernet switch or by a Wi-Fi base station, nobody should have to keep track of what's out the MAC addresses. Nobody has to, but you can if you want. So you can disable ARP by inside your Ethernet switch, for example. You can kill all the ARP packets or capture them, and instead of broadcasting them, you can decide to send them to a directory service if you have this directory service, which you have typically in managed networks like banks or enterprises, where you cannot come and plug your PC to an Ethernet socket. You can plug only one specific PC to one specific Ethernet socket, and somebody knows which PC should be where and has written in a network management application the MAC address that corresponds to that. At EPFL, we don't do that because if I change my PC, I connect to another office, it works. But if you try to do that in more managed environment, it won't work. We'll talk about it in a minute. That was for IPv4. IPv6, as usual, is the same, but more complicated in terminology. The idea is exactly the same, so there's no difference from that viewpoint, except 2 things. The first one is broadcasts are taboo in IPv6. In IPv6, we never use broadcast. It's a design philosophy. Broadcasts are, of course, a bit uncontrolled, so the designers of IPv6 decided whenever we can, we will try to get rid of the broadcast. So here, it's replaced by something that is called a multicast. So what is a multicast? A multicast is like a broadcast, except it's not for anyone, it's only for those who are member of a given group. We'll talk a bit more about IP layer multicast a bit later. But right now, if you remember, there are IP addresses, in particular those, for example, with IPv6 that start with FF. FF are multicast address. Multicast addresses are addresses of a group. Now, how does it work? Well, for a machine to receive it, you need that the machine is programmed to be active member of the group. So you need to configure the machine to say, you should listen to this group and receive the data. For IP multicast to work, you need also the routers to know which group should be forwarded where. But here we're discussing of multicast that's inside the local area networks, so the routers are not concerned. The thing that, so that's the first difference that there is with ARP in IPv6. We don't use broadcast addresses, that's the essential difference. The other less essential difference is we change the terminology and the protocol layering. It's not called ARP, but it's part of what is called the Neighbor Discovery Protocol, ND or NDP. And the packet, the ARP packet, which many people continue to call an ARP packet, is inside an IP packet. So it's not a native Ethernet packet that lives outside the IP world. It is inside an Ethernet an IP packet as part of the ICMP. ICMP is the Internet Control Messaging Protocol. We discussed that last week. When you send an error message relative to the IP layer, it's an ICMP message. So here is the same. It's not just error. It's all the management of the IP layer that is now put inside ICMP. So it's cleaner, but for us, it's essentially anecdotal. It won't change anything. Except we need to analyze those addresses, which is more a nuisance than anything. So the multicast address of interest is what is called the solicited node multicast address. So it's the same exercise as before. This machine wants to know who has this IP address, the one that's here. Voilà, that's one here. Instead of sending a broadcast, it will send a multicast to a group. And who is that group? That's the group of all people who have an address that have the same last 24 bits. So we take the last 24 bits of the target IP address, the one that are in red here. We put them to a well-known prefix. That's always the same. That's the black part. We add those 24 bits, and that gives us an address that is a multicast address. Now, who belongs to that group? All machines that happen to have an IP address that has just the same 24 bits at the end. Now, because the final bits of an address are the least significant ones, they are in some sense random. So inside the same network, plus they are usually the host part. So inside the same network, there is probably how many machines having this address in that group inside the local area network? There's probably just one. Except if the host part would be less than 24 bits, there might be several. But if the host part is at least 24 bit, which is quite common, there's only one. So it's a multicast in some sense, but it's in fact, with high probability, there will be only one. Now, the trick is, of course, we need the Ethernet switch to be able to send this to all the systems that belong to the multicast group. In practice, low-level switches, the cheap one, they don't know how to do multicast. So if you're an Ethernet switch and you receive a packet that's multicast, you don't know who belongs to the group, so what do? You broadcast it. So in practice, it will be broadcast by the switch, but the Ethernet adapter will still analyze the destination address and they will stop the packet immediately. So the details sometimes are less different than the theory. So this ARP request, which is called a neighbor solicitation, otherwise is the same, will be received by STI Sun1, who will receive it, and after that point, everything is very similar to the IPv4 case. Here is an explanation that I will leave you to be able to answer a bit later. So how do we extract the 24 final bits? Well, to do that, you need to go through the uncompressed form of the address to understand where the 24 bits are. And remember that one hexadecimal digit is 4 bits. So you need 6 hexadecimal digits. And you add this to this prefix, which is the multicast address called the solicited node multicast address. You compress it, and this is how you get this one. And after that point, this is what I said before, the same as with IPv4, and in particular, the address will be kept in a cache that will be refreshed only if there is no traffic flowing between the two interested parties. In IPv4, we can see the address resolution protocol. This is a Tcp dump, which is a similar thing as a Wireshark display of a packet. We find the destination address being broadcast. The source address is, of course, not broadcast. The source address says here Apple. It's a Macintosh that has sent this. Apple is not written inside the source address. How do we know it's an Apple device? Yeah?
It's one of the address that were assigned to Apple?
Yes, so the MAC addresses, the first half of the MAC address is called the organization unique identifier, is assigned to a company. And there is a database published by IEEE of who has what, so this database is available in this software. And we see that's an address resolution protocol. So the hardware type, which is an IP-centric terminology so you have to be careful with the terminology, which is sometimes different depending on who writes the code and who writes a paper. Hardware, in the context of ARP, means local area network. So IP views the world as hardware systems being connected to itself. It's a bit more than that. Typically, the MAC layer functions are in fact performed in hardware in most machines, and IP layer functions are performed in software. But this is not cast in stone. I mean, some devices, some companies are building TCP IP on a chip for embedded computers, embedded devices, for example. But you will often find this, that hardware means layer 2, MAC. So here the hardware type means the protocol type inside the Ethernet packet. And here it says Ethernet and it says ARP, sorry. So the protocol type will say ARP. And all the text that is here is contained inside the ARP message. So protocol type IP is not an Ethernet protocol type, but it's inside the ARP message. It is saying, I'm trying to find a destination address, and the protocol type is IP. Because ARP at the origin the idea was that it would work for all kinds of protocols, not just for IPv4. So we could have used the same ARP for IPv6 or IPv4, but it has not happened. But we do find this in the details of the packet. IPv6, the terminology is a bit different. The ARP packet is an Icmp packet, which we find here. It's called an Icmp. There is no Icmp v6, in fact, it's the Icmp used with IPv6. But other than that, we should find exactly the same as we know. So this was a trace done on my computer. So we found that the destination address is the solicited node multicast address. That's the IP destination address. So the address resolution request is contained without an IP packet with IPv6 and sent to a multicast address. And the target address, which is partly hidden by PowerPoint stuff, is that one here. And we find the last 24 bits are 1, 1 here. Yes?
Just for the ARP packet, for the hardware type, apart from Ethernet, what do we have as type of that? Would it be written wireless if we were over a wireless LAN?
Yeah, it would be Wi-Fi. Or it could be Zigbee, or 802.14, or token ring, or field bus, or whatever. The most widespread wired thing is Ethernet. The most widespread wireless is Wi-Fi, but there's a zoo of possible things, in particular in the industrial environment. There's lots of different layers. Now, does this poll? Yes, I do have a control panel here. It doesn't show on the screen, but it seems to work. So if you don't have a clicker, by the way, you should have one. So those of you who didn't have clickers at the clicker test last week, we lent them clickers, but we will give the grade only when you return the clickers. So as an incentive to get your own. So here, a small question. ED2 minus IN has a packet to send to LRC Sun S, and we observe the packet at the source. What is the destination MAC address? So we observe it at the source here. I close in 5 seconds.
It's not closed yet.
It's not closed, yeah. Bad luck. Now it's closed. Thank you. And does it display? Yes. Okay. That's, of course, the correct answer. It's a repetitive question, right? I've asked it several times. Of course, this is the correct answer. You send to the MAC address of the next hop. So all the ARP we saw in an example where the destination address was also the destination MAC address. When you're a router and you send, you do also ARP and all the like, but for the next hop. So ED21 will do an ARP request to find the MAC address of the router. Because if you remember what you've done in configuration, in configuring in the lab, you've never given a MAC address of a router, for example. You give the default route, but you don't give the MAC addresses. Question?
Is it just for the sake of the question that the router LNINR has 2 different MAC addresses? Or does that happen normally as well?
Well, of course, it has 2 MAC addresses because it's a router, it has 2 interfaces. So it has 1 MAC address on each of the interfaces.
But isn't also MAC addresses, don't they depend on the hardware itself? Like
Yeah. So this router, the question is why does it have 2 addresses? Is it a bug, as in some of my quizzes, or is it intentional? Here it's intentional. It has a green and a red interface. It has a MAC address for the red and a MAC address for the green. When ED2-IN does an ARP, there's no way it gets any information about the green LAN. So we'll get only information about the red one. As you can easily imagine, of course, this protocol is a bit primitive, and that's one of the problems of the TCP IP architecture. It was developed in universities with people that are a bit sophisticated and bizarre sometimes, but not bad for most of them. So they didn't thought of attacks. Strange enough, TCP IP architecture was never thought with security in mind. So security always comes as something we have to add. The ARP is one of the protocols that's easy to attack. If you're in a hotspot somewhere and you can inject false ARP replies, you can impersonate another machine and get all the traffic for that machine. As easy as that. Right? So if you are faster than STI-SUN1, or if you are, let's say, a brute force attack, you could simply flood the system with ARP replies. Then you will get, with some probability, you will be able to catch, to be faster than STI-SUN1 and respond before it. Yes?
If we manage to get the traffic from a free impersonate machine, and we manage to get traffic from somewhere else, what happens to the original user? What does he get?
Nothing. So assume this guy, this bad guy, manages to send the correct reply to this, then this one believes that the MAC address of STI-SUN1 is this one. So all traffic from ED2-IN to that STI-SUN1 will land up here. So it will come here. Now, of course, if that's the end of the story, probably the only thing you will have achieved is a denial of service attack. You will break the connection because the flow of traffic to STI-SUN1 will not reach STI-SUN1. But you can be a bit smarter. You can here copy the traffic and then send it to STI-SUN1. So do a man-in-the-middle attack. And then you will be able to create more damage. Yes? Question? Yes, so the question is what happens if you receive from both of them? Then it depends what the software will do. If you are a well-managed software, you start receiving various replies with high frequency from various machines, then you will think something is going wrong. And perhaps you will stop, you will decide that this destination, it's safe to drop this destination. Whether all, but you can try in the lab, you can try what happens. I think many machines do nothing. They just take the last one received. So this is called ARP spoofing, impersonation of a machine in the ARP protocol. Yes?
Sometimes the ARP spoofing is misdirected, like if an antivirus detects that two IPs have the same IP license configuration, and an antivirus can detect this as an ARP spoofing. How can we see if it's really ARP spoofing?
So the question is, it could be not a malicious guy, but simply a bug, that the two machines do have the same IP address. In that case, it should be the same conclusion. I mean, the communication should not work. If you have two machines that have the same IP address in the same LAN, it's not intentional. They're not in private LANs that are not supposed to communicate with each other. If they're in the same LAN, you remember the principles of IP. Every interface has an IP address. If you have two that have the same, you're violating the principle, so something will not work somewhere. So the best thing to do is to refuse talking to those guys. Normally, when you, as we will see in one of the examples later, when you acquire an IP address, you do what is called an address duplication test, where you broadcast in your LAN for IPv4 the information that you have this IP address, and this by sending an ARP to your own IP address. If somebody responds, then you found someone else has the same address as me, then I stop working. But not always, not all devices do that. So there is a security issue with ARP, which is not solved in, I would say, in Wi-Fi hotspots or in non-managed Ethernet environments, which means that you have to be aware of it, and typically you should not send, well, you have to imagine always that there can be a guy in the middle in your network, and use appropriate encryption everywhere. In managed environments, we use a zoo of things to prevent that, which is essentially a combination of what is called DHCP snooping and dynamic ARP inspection. Dynamic ARP inspection is what I had mentioned a second ago. Imagine you have an Ethernet switch which has some intelligence. Then the Ethernet switch receives all those ARP requests. So what it could do is capture them and try to answer them directly. That's called dynamic ARP inspection. Now, how can it answer them? It needs to know the information. So it could have the information from a database that's done by network management, that exists in some cases, or it can also get it automatically by connecting with a DHCP. So DHCP is the protocol that we will see in a second that's used for automatically allocating the IP addresses. So it can learn by snooping, that means listening to all DHCP traffic, what are all the valid addresses, and then it can check whether it's allocated only once and then respond. So if we do this, then we will avoid the problem of ARP spoofing, providing that the first phase is correct, so nobody is cheating with DHCP, which is another story. So this is commonly done, I would say, in banks, in enterprises where you care about some level of security. Now, a quick other question that seemed to work. I'm showing here a small network with two Ethernet concentrators and one router. P.H1, this machine, sends a packet, has just rebooted and talks to Q.H1. Perhaps it is its DNS server. And it's the first time it ever speaks to that machine. It ever speaks to anyone. What will P.H1 send an ARP for? For which address? I propose two solutions, none of those, or a wildcard. I close in 5 seconds. Try to close. Ça marche. And the majority, this is reassuring about democracy, the majority is correct. So this is the correct answer. An Ethernet concentrator is a device that makes a LAN out of all the devices concentrated to it. We call it a switch. It could be a hub, we'll see a bit later. So M1 has a packet to send to M3. Well, it will need to go to the router because the final destination is in the same LAN. So we'll look for, you will send the packet to the router. In order to send to the router, it needs to find the MAC address of the IP address of the router, which is in the same LAN, which is P.1. So it's always the same question, but it is so important that you have to make sure you get it right. That is ARP. So ARP is really one of the very, very special things of TCP/IP that creates a lot of trouble and everywhere. So we need to, this is why we saw it with some detail. Question?
I thought the ARP request a broadcast that you send it to everyone, like who is that, etc. So how can it send to P1? Because I thought ARP requests were always like broadcast.
I didn't say 2, I said 4. So the ARP packet is not sent to P1. It's an ARP for P1. So I'm looking for P1. Yeah, thank you for asking. That might have been misunderstood. So it's a broadcast packet if it's IPv4, or this bizarre multicast, solicited node multicast address in the case of IPv6, in which case it will be probably 2, P.1, and or broadcast by everyone if the Ethernet concentrator doesn't do anything else than broadcast. Yes?
Why doesn't he send to everyone? Why doesn't he just ask because this IP address?
Why doesn't he send to?
Why doesn't he send to everyone? I don't understand.
To R1? To everyone. The R packet is sent to everyone inside this domain. And it is for P1, that is inside the question, there is who has P.1. That's what it means. But you are right, M2 will receive it. And if M2 is not bogus, it will not do anything, will drop the packet.
Yeah, for me it's just like he can't send it to P1 because he doesn't know him. Like he sends it for everyone.
Correct.
Intention, so for me it's
That's correct, yeah.
none of the above.
It was not?
One was none of the above because P1.
Oh, none of the above, okay. But it's not graded today, so it's, we don't need to discuss that. Well, here it's, I mean, literally, it's an ARP packet for P1. 4 rather than 2. That was ARP. Another thing that is very annoying in IP, the IP layer, is, so the annoying thing is that there is the MAC layer. That's the first problem on IP. The second thing is we need to configure IP hosts, as you have experienced already. What do we need to configure? Well, we need to do all those things that are written here. An IP host needs to be configured with its own IP address, with the mask, because the address itself doesn't say what is the network portion, what is the host portion, and a few additional information. 2, the IP address of the default router, or in general the routing table, but in a host in most practical cases the routing table inside a host contains only one line, which is the default router, and the IP address of the DNS server. In order to resolve names, we need the IP address, not the name, of course, of the DNS server. You can always do it manually, and we've seen in the lab how to do that, or automatically. Of course, everybody prefers to do it automatically, and the way to do that is called DHCP, Dynamic Host Configuration Protocol. In IPv4, as usual in IPv6, there is also the same thing, but much more complicated, that we will see in a second. So DHCP it came as an afterthought. It was invented in the 90s, so 15 years after IP was invented. So before that, people typed in addresses. Right? And then when the internet went public, people realized, well, we can't ask people to type in addresses. So the way it works is a bit like ARP, is very simple. I have a PC that boots, and this is, for example, I'm doing it at EPFL. So this is the router to which the Ethernet segment is connected. At home, it might be my so-called ADSL modem, which has usually a router function. Then if DHCP is enabled in the configuration of my host, which is for many hosts by default, whenever it boots, it will ask for an IP address and the additional configuration information by sending for a DHCP packet, which is called, in that case, discover. Now, what is it? It's a packet that is an IP packet, which is sent to the broadcast address. Is UDP. It's a single message with the UDP ports allocated for that. And with a source address, which is 0. So you remember, all ones means broadcast, and 0 means absence of address. So that's one of the very few instances where you can see an IP packet with 0 as the source address. Of course, it has no address. It's trying to acquire one. Why is it done this way rather than the ARP way? I don't know, to be honest. And we could have done it like the ARP way. You could have sent a packet, which would be just a MAC layer packet. So this packet is received by whom? Well, it's received by everyone, but it has a port number here. So it's received only by the machines that are listening on this port number. We'll talk about the transport layer a bit later, but the way the transport layer works is you require one of the machines to be listening on a given port number for communication to happen. The listening machine is called a server. So this works only if on the local layer network there is a DHCP server. So if there is, assume this is a DHCP server, very often the box that is called router also contains a DHCP server. Then the DHCP server will get this reply, this request. We look in its table, what is the block of available IP addresses that somebody must have configured for me, or I use a default block if I am an ADSL modem. I will pick the next available IP address, and I will reply and give the message back to the source. Here. That is the basic operation. So I'm not showing all the messages. We've done it for ARP, so you can imagine easily how it's very easy. But what I've illustrated here is the case where the server would be here. And this is what happens if with your ADSL modem at home. You have a DHCP server in it with a block of address, which is probably 192.168 dot something, and you will receive the next available address. The address is kept by the DHCP client, by your PC trying to boot. And like ARP, there is also a timeout. After some time, the so-called lease will expire, so it will need to refresh it by asking again. So this is in order to avoid keeping addresses of machines that have disappeared, keeping them forever. Now, the interesting point is very often in larger networks like at EPFL, there is not a DHCP server in every router. Why not? Well, because router is an IP layer forwarding function. A router is by definition a box that forwards packet by analyzing IP headers. Whereas DHCP is more a network management function. It is deciding who should have which address here. So typically you put that in a server, in a computer, not in a router. So typically you have, and that's the case at EPFL, the DHCP server is not in the router. Well, in that case, it will still work if the router performs a function that I call Dhcp Relay, which strictly speaking is an application layer intermediate system function. It's application layer because it's receiving things over UDP. So this is a small code that is really an application. And it's a relay or intermediate system in the sense that it's receiving requests of a given application, in this case DHCP, and are forwarding them further. a bit like an email server receives a mail from someone and sends it forward. So it is a relay function, and if we want to be strict in terms of layering, it's application layer relay. Then if we have a router here that receives a relay function, what it will do is it will forward this message to the DHCP server, while and the DHCP server will know now by analyzing the IP source address of this machine where it is coming from. Therefore, we'll know on which LAN also I can allocate the address, and we'll send the response back to the relay router, to the DHCP relay. So if I analyze those responses here, what will be the IP destination address? That of the router. In fact, it's the box that we can call router, but in fact it's the address of a host, which is the DHCP relay that is sitting inside the router. So here I'm making the difference between a physical box and a function. There's a function called DHCP server, which we can view as a host, an application layer program, or a DHCP relay that is sitting in the router. But if you talk to most people, they will say, well, that's part of the router function. But at least to understand things at the beginning, it's better to differentiate functions, even if they are in the same machines. So this one will receive it. Now it has an IP address in the reply, so it's able to respond as if it would be the server. The main difference is that this relay function has no state information. It doesn't have a database of all the blocks of IP addresses that need to be relayed. It just does a very stupid job of forwarding on one hand and repeating on the other hand. If we analyze the IP destination address here, what should it be?
0.
It will be 0, right? It could be the address that is proposed, but this address is not yet verified, so this address is not yet allocated. So this is a 0 destination address. Will it work? Can you send an IP packet with 0 destination address? Yeah.
Another transition ID, something like this, because two hosts may not.
If it's a question, not an answer, I'll take it later. So here, the answer is yes, you can, but it works only in the local area network. Of course, this packet will not be forwarded by any router. So it works because the MAC destination address will be the correct MAC address. So this one, when it has received the reply, it needs to remember the MAC source address of the reply. The MAC address is also put inside the DHCP message. So when it receives it, it can also use the MAC address that is in the message here to send the information here. Voila, that's the end of this first hour. Now I can take your question.
Is there another ID transition or something like this? Because in addition to IP, because two hosts may demand IP address at the same time. How will they be differentiated from?
Well, they all have different MAC addresses.